Alright guys, so over the last few days we've been talking a lot about vocabulary that we associate with graphs. Things like critical points, points of inflection, increasing, decreasing, concave up, concave down, maximum, minna, etc. Today what we're going to do is put that all together into one big problem and sort of see how we can use all of this information to actually make the sketch of the original graph based on what we have. So if I told you, hey, sketch me a picture of x cubed minus 12x minus 5, you guys would probably say, well, I know it's a cubic, but other than that, it's pretty hard to sketch that picture without some more information. So what we're going to look at today is how to use all of this other information to actually make a very complex and accurate picture of the graph. So if I give you a problem like this and I say, tell me all of this information and sketch a graph, you're going to start immediately by just taking the derivative. So the first derivative of this equation would be 3x squared minus 12. Then you're going to make that derivative equal to 0. And you're going to solve. So I would factor out the 3, and I would have x squared minus 4. I would continue to factor, and I would get x plus 2 times x minus 2 equals 0, which means my zeros would be x equals negative 2 and 2. As soon as I have those numbers, I can immediately write them down and list them as the critical points of the function. Next, I would take the second derivative. So that would be 6x, and I would make my second derivative equal to 0, which in this case, for step number 4, would just give me one answer, x equals 0. Now, I'm tempted, I really want to just write down x equals 0 here where it says points of inflection, but I can't do that yet because in order to be the point of inflection, not only should the second derivative equal 0, but it actually has to change signs at that value. So I'm going to hold off on that until after I make a chart and see if my signs actually change. So let's make a table. What we're going to do here is make one big hybrid table where we combine all of the information about the first and the second derivative so we can get a really accurate picture. So it doesn't give me a specific interval here, which means I'm going to start with negative infinity, and then I'm going to list all of the numbers from my critical points where my first derivative equals 0, and all of the numbers from where my second derivative equaled 0 in this table in order. So I would have negative 2, 0, 2, and infinity. Now this table is going to have two rows in it. It's going to have a row for the first derivative and a row for the second derivative. You may remember making tables like this when we learned position, velocity, and acceleration. We said we're going to put all of the velocity stuff, which is basically the first derivative, in the top row, and we're going to put all of the acceleration stuff, which is basically the second derivative, in the bottom row. We're doing the same thing here so we can compare all of that information. Next, what I'm going to do is take numbers from each of these sections, plug them into the factored version of my first derivative, which would be here, and I'm going to see if I get a positive or a negative number. So if I plug in negative 3, for example, 3 is always positive. Negative 3 plus 2 is negative, times another negative would make it positive. And I'm going to draw in an arrow that goes from the bottom left to the upper right to show that my graph would be going uphill for that section. Now I'm going to plug in negative 1. So I'm going to have a positive times a negative, which is negative, and I'm going to draw in an arrow going from the upper left to the bottom right to show that my graph would be going downhill. Next, I'm going to plug in positive 1. Positive times a negative is still negative, so I'm going to draw in an arrow going from the upper left to the lower right to show that my graph is going downhill. And then I'm going to plug in positive 3. So positive, positive makes positive, and I'm going to draw in an arrow going from the lower left to the upper right to show my graph is going uphill. Now I'm going to work on my second derivative. So remember, we're going to plug this into our factored version, which for this one isn't really a big deal. It's just 6 times your number. So if we plug in negative 3 times 6 is negative. So I would be concave down like a frown. It's very important to draw these pictures accurately. Next, I would plug in -1. So if I plug in -1, I get a negative, again, concave down like a frown. Next, I would plug in +1. So again, +1 times 6 is positive, up like a cup. And plug in a +4, positive times 6 is positive, up like a cup. Once you have all of that filled in, it's a lot easier to fill in the rest of this information down here. So let's talk points of inflection. I said before, I really want to write the x equals 0 on this line, but I can't till I see if the concavity actually changes signs. Now, based on this table, I can see it did change from concave down to concave up at 0. So I would say x equals 0 is my point of inflection. Now, for increasing, I'm just going to look at the first row of my chart. Am I going uphill or downhill? The first section that's going uphill is -infinity to -2. And the next section that's going uphill is from +2 to infinity. Now these two middle sections are both going downhill, and what I can do to make it easier to write my answer is actually combine those into one big chunk of information from -2 to +2. Next, I'm going to look at concavity. So for this, I'm going to use the second row of my table. Concave up would be wherever my second derivative was positive. In this case, these last two sections were both concave up, so I would combine that and make one big section from 0 to infinity. Concave down would be the first two sections. So in this case, I'm going to combine that, and I'm going to make it one big section from -infinity to 0. Next, I'm going to list my maximums and my minimums. And while I can tell this from the chart, I do think sometimes it's easier to tell this when I have a picture. So from the chart, I can tell I go from uphill to downhill, so this would be a max. From the chart, I can tell that I don't change directions at the 0, so nothing is happening there. And from the chart, I change from downhill to uphill at 2, so this would be a min. I'm going to wait and confirm that in my graph before I actually list it in my list of information. Now, the only other thing we need to make a really good graph of this function is some y values. So some actual like input-output pairs that I can graph to get a really accurate graph. So to get those values, what I'm going to do is take all of these x's and plug them into my original function. That's going to give me some y values that go with them, so I have some points to graph. So if I plug the number -2 into the original problem, I get -8 plus 24, which is 16, minus 5, which is 11. If I plug the number 0 into the original problem, I get -5. And if I plug the number 2 into the original problem, I get 8 minus 24, which is -16 minus 5, which is -21. So based on that information, I can tell the highest y value that needs to be on my graph is 11, and the lowest is -21, which means when I sketch my graph, I'm going to make sure I can accommodate those numbers. So I'm going to leave a little bit more space below the x-axis than above. I'm going to count by 5s for the ease of graphing. So I'm going to have 5, 10, 15, -5, -10, -15, -20, -25. My x values, the important ones are -2, 0, and 2. So I'm going to go 1, 2, 3, 1, 2, 3. Now I'm going to start with graphing the ordered pairs. So I'm going to go -2, 11, put a point there. 0, -5, put a point there. 2, -21, put a point there. Now I need to fill in what the graph looks like between those numbers. So I'm going to use the pictures in the chart to help me. The first chunk of my graph should be going uphill, but be curved in a concave down fashion. In other words, it should look like this. Now the reason this arrow is pointing down is that I'm still going uphill from left to right. It's just that I keep going towards infinity. That's why there's an infinity there. A lot of students make a mistake here and they're like, hey, isn't this downhill? But remember that we always read a graph from left to right, just like when we read a sentence. If I go this way, I'm going uphill. Then I'm going to go downhill and be concave down. So I'm going to connect this like this. Then I'm going to go downhill but be concave up. And then I'm going to go uphill but be concave up. And again, I drew an arrow there because I'm going to continue going forever. That's what infinity means. Now, based on this graph, I can confirm that there is a maximum here and there is a minimum here. Just like I noticed in the table, it's just that this confirmed my suspicions. So, I'm going to have a maximum at x equals -2 and a minimum at x equals 2. Let's go ahead and try this one more time to make sure we go through this process. It is a process you need to follow, so it's good to practice it kind of more than once so you can see the pattern of what we do. So for problem number 2, we're going to start the same way. We're going to start by finding the derivative and making it equal to 0. So I would have 4x cubed minus 12x squared, and then I would make that equal to 0. That's step 2. I would factor out a 4x squared, and I would get x minus 3. And then I would solve that, and I would get x equals 0 and 3. Next, I would take my second derivative, which would be 12x squared minus 24x equals 0. And I would make my second derivative equal to 0. So I would factor out the 12x, and I would get x minus 2, and I would get two numbers, 0 and 2. Next, I would make a table. In my table, I'm going to include all of the points I got from my first derivative being equal to 0 and all the points I got from the second derivative being equal to 0. So I'm going to start at -infinity, and then I'm going to put these in order. So 0, 2, 3, and infinity. Now my table is going to have 2 rows, because I'm going to have 1 row for my first derivative and 1 row for my second derivative. And again, this should remind you of what we did with velocity and acceleration. So my first derivative will go in the first row, and my second derivative will go in the second row. All right, let's plug in some numbers. Remember, we're going to plug our numbers into our factored version of our equations. So if I plug in -1, something squared is always going to be positive, so I don't really need to worry about that ever. I'm just going to have -1 minus 3, which is negative, so my graph is going downhill. Then I plug in +1. Positive, negative, still negative. My graph is going downhill. Then I plug in +2.5. Positive, negative, still negative. My graph is going downhill. And then I plug in +4. Positive, positive. Now my graph is going uphill. Now let's take a look at my second derivative. Again, I'm going to plug it into the factored version of my equation. If I plug in a -1, I get a negative times a negative, which is a positive, so I'm concave up. If I plug in +1, I get a positive times a negative, which means I'm negative, so I'm concave down. If I plug in 2.5, I get a positive times a positive, which is positive, so I'm concave up. If I plug in +4, I'm going to have a positive times a positive, so I stay concave up. Remember, these pictures are really going to help you, so I would be really meticulous about drawing them nicely and neatly. Critical points. I can fill in the 0 and the 3 right away. Points of inflection. I need to check to make sure that the concavity actually changed at 0 and 2, which based on this chart, it does change from up to down and then down to up. So I would list both of those here. Let's say that it didn't change one of those times, then I wouldn't list them both. I would only list the x value where the concavity actually changes. For increasing, I'm going to look at row 1. Increasing would only be from 3 to infinity. Decreasing would be from -infinity to 3, and I can group all 3 of those sections together because they're all decreasing. Concave up, I'm going to look at the second row of my table. So concave up is going to be from -infinity to 0, and then also from 2 to infinity. And again, I'm chunking those together because they're the same. Concave down from 0 to 2, or I'm sorry, from 0 to 2. There we go, I said it right. Maximum and minimum locations. Well, based on the chart, it doesn't look like I have any maximums, but it does look like I have a minimum at 3. So I'm going to hold off to list them until I actually see my graph, but it kind of seems like that's what's going to happen. Now let's go ahead and get some actual y values. So when I plug in 0, I get 0. When I plug in 2 to the original function, I get 16 minus, it will be 4 times 8, so 32, so negative 16. And when I plug in 3, I get 81 minus 4 times 27, which is 54. Is that right? 981, and then this is 27 times 4. Oh my gosh, that is not right at all. Okay, I'm going to use my calculator for this one, just to make sure I don't screw this up in a high pressure situation like a video. So here we go. If I use my calculator just briefly for this one, I'm going to have 81 minus 4 times 27, which is negative 27. There we go. I just don't want to make a mistake on a video. All right, so if I had more time, I would have worked that out by hand, but I want to go ahead and finish this up so you guys can be done. So now I'm going to look and make a graph. So I can see that my y values are all negatives or zeros, so I'm going to focus on the lower part of the graph. I'm going to go ahead and count by 5s again, just to make this all fit nicely. Bloop, bloop. 5, 10, 15, 20, 25, 30. The x's are going to be 0, 1, 2, 3, 4. Okay, let's graph our points first. So 0, 0, 2, comma, negative 16, 3, comma, negative 27. Now let's connect the dots. So I'm going to go downhill and be concave up. So I'm going to be like this. Downhill and concave up. Then I'm going to go downhill but be concave down. So like this. Then I'm going to go downhill but be concave up again. Then I'm going to go uphill and be concave up again. Now based on this, not only is x equals 3 a minimum, it is the absolutist minimum. So if I did need to specify the absolute max and the absolute min, I would have written that in. For maximum locations, you would say none. For minimum locations, you would say x equals 3, and you would be done. Okay, I hope all of this makes sense. I hope it you can kind of see how this all fits together, and we will definitely practice this process of graph sketching tomorrow when I see you in class. Thank you guys so much and have a wonderful day.